So on the screen right now, I have two similar triangles. I created this with a dilation like we did in class previously. You can see I did a dilation of 1/2. So this was my original ABC, and the A prime, B prime, C prime is a dilation of 1/2. So I definitely know, because of the way I made it, that these are similar due to they all have congruent angles, and if I measured all the sides, they'd have a ratio of 1 to 2. Okay, so you can see they're similar. And again, sometimes this gets confusing because I have people say, well, if I know these angles are congruent, don't I know the triangles are congruent? And I'm trying to show you an example here of here's a triangle with 3 angles congruent to 3 angles of another triangle, and they aren't congruent. Okay, they are similar. So there is a difference, and I know we struggled with that a little bit before. So in 7.4, we're talking about actually just one postulate for similar triangles. It's called the AA similarity. And the way you can write that is the AA with the squiggle next to it. And it says if 2 angles of one triangle are congruent to 2 angles of another triangle, then the triangles are similar. Okay? So again, you could write that as AA similarity. If once you know the 2 angles are congruent to 2 angles of another, you know the third angle has to be equal. So all you need are 2 angles. And again, notice this works for triangles. Now, I wrote, why can't you use something like the AAA similarity postulate for quadrilaterals? We are going to discuss this question in class. So I do want you to think about that and think if that would work. I mean, if I know 3 angles of one quadrilateral are congruent to 3 angles of another quadrilateral, doesn't that prove they're similar? Is that enough? Because it's enough in a triangle. And why would it work for one? Does it work for all? Or if it works for one, why doesn't it work for the others? So when I go to the proof here, I have AC is parallel to BD, and I'm just showing the triangles similar. So in your statements and reasons, I think I'm going to need to type this because it's going to be hard. I need to change the color for you. Do it in blue. Okay, I have my given. Okay, I also know that it's hard for me to use the symbols, so AOC is equal to angle DOB because of VAT. So I also know, because the lines are parallel, you could do a couple different ones here. I could say angle C equals angle D, and the reason for that would be, oops, sorry. If lines are parallel, and again, you guys would probably use the abbreviations, then alternate interior angles are congruent. Now that I've shown 2 sets of angles congruent, just click back here to show you that. I've shown these angles are congruent, and these angles are congruent. I have enough to prove they're similar. So note the difference between similar and congruent. So now I can say triangle AOC is similar to triangle BOD by AA similarity. So it's as simple proof as that. You just need to be able to prove 2 sets of angles are congruent. Okay, over here, try and do this again with typing. Okay, I have my given. I also know that angle 1 is congruent to angle 2. So in this one, I know they're perpendicular, but that's going to make me, I do have to write a little more to prove the angle is congruent. So I can say angle AHR equals 90 and angle FBA equals 90 by definition of perpendicular lines. Then I can say angle AHR equals angle FBA. And you could say substitution or transitive property here. Both of them work because they both say that. Okay, I was already in the given that angle 1 is congruent to angle 2. So now I can prove triangle ARH is similar to triangle, let me make sure I use my corresponding parts correctly, FAB by AA similarity. Now notice that's not exactly what I was trying to prove, so I have a little bit more to go. Next, I can say that, and I'm going to choose the sides that are right here. So I'm going to choose something with HR. So I know HR would correspond with AE. No, wait, is that right? HR corresponds with AB, sorry. Is that what that says? Okay. And let's see, AH corresponds with FB. Okay. And that is because corresponding parts of similar triangles are proportional. Once I know that they're similar, I know their sides are in proportion. So notice this is in CPCTC, that's a little different. And then I know that HR times BF equals BA times HA. That's a property of proportion. All I did there was take the, let me move this up for you, is take the proportion I had here and I cross multiplied, and the properties of proportion say that I can do that. Okay, so this would be the proof for this figure, proving the triangle's similar, and then using the fact that they're similar to prove something else. Okay, over here are the triangles similar. You can try this, push pause, try it, and then you can come back. All right, in the first one, I'm given that these lines are parallel. So I know these are congruent by corresponding, and these are congruent by corresponding. To be honest, I could have done even this one by reflexive. So the large and the small are similar, yes. Over here, this is a pretty direct one, 1 to 1, 2 to 2. Yes, by AA similarity, they are. Now the one down below, there's a couple different ways you can look at this. I'm going to actually do it one way, but like I said, there's more than one way to do it. If you remove this for a second, what kind of triangle is that? Hopefully you're saying isosceles. So we know these are equal by ITT. Now when I move that back in, look at that. AA. So these are similar by AA similarity. So this is a yes too. And again, there's more than one way on that one to do that. These are actually even congruent. You'd be able to prove them congruent by SAS, with this being the reflexive. And if triangles are congruent, they are similar. Their ratio is a 1 to 1. All right, this triangle over here may look tricky. They're not parallel. I have these sets of congruent angles, but don't forget, look, they both share this angle. So by reflexive, they both have this. So the angle, 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 angle. So these are also similar. So that is also a yes. But don't forget, look, they both share this angle. So by reflexive, they both have this. So the angle, 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 angle. So these are also similar. So that is also a yes. This is a redo of the last part of the 7-4 notes. So we're comparing, we know these figures are similar with the AA similarity. We already did this. So when you set this up, make sure you do side of the small over side to the large. Okay, so again, 5 is the side of this small triangle, and 5 plus x is the side of the large triangle that it is similar to, equals 3, the side of the small triangle right here, to the entire length of the large triangle, 4. So I get 20 equals 15 plus 3x. That was just me cross multiplying. I skipped a step there, but I think you can handle that. 5 equals 3x, so x is going to equal 5/3. Okay, for the bottom one, which is the one I messed up before, I'm going to set up the proportion. So here I have 3 as my small side. My large side is x plus 3. For this, I have 4 over the entire side, which is 7, equals y over 8. So notice across the top and all the numerators, I have the sides of the small triangle and the denominator the sides of the large. You can cross multiply. I'm going to do the 4/7 and the 3 over x plus 3, so I'm going this way. Sorry, that's an equals, not a z. Okay, so we get 4x equals 9. So x equals 9/4. Equals. Okay, make sure I have the math right on that one. Okay, and then when I go this way, remember this is a y. I get 7y equals 32. Oof. And y equals 32 over 7. So hopefully I did that right this time. Okay. Okay.